Hey folks, sorry I had to interrupt the flow of that, but I realized that I didn't introduce you to the periodic table properly first, and the I used to lecture this like the books lecture, teach this, and then I would teach you a better method of doing it. But since I've just gotten rid of the book for this course because it really wasn't just not worthwhile. Uh, I don't need to teach that stupid book method that doesn't work. All right, now first off, I'm going to teach you a bit of information about the periodic table, and I'm going to come back to this, okay? So sorry this is a bit sort of abrupt in jumps here, but I just realized that I never fixed this organization since last semester. Um, now, let's do the periodic table, and then I can mention about doing electron configurations. So the periodic table is considered by many to be the most predictive tool in all of chemistry. Really, for a basic intro level chemistry, as long as you understand how to truly use and understand what the periodic table is actually telling you, you know enough to do damn near everything you need. It's an amazingly powerful tool. It is composed of vertical columns that we call groups. Some people have called them families. That's not really right, but groups is the actual terminology. And horizontal rows that are called periods. Now, these periods, many people are going to call them energy levels or shells if they understand what they're looking at. And that's because, remember how I was talking about energy levels and shells before? I just went into this. Well, those periods are literally the energy levels and shells I was talking about before. The shape of that periodic table all this time was due to those electron configurations. Those are literally the addresses for the electrons on the periodic table. Okay? So your groups, these are going to be your vertical columns in the periodic table. The groups are going to contain elements that have similar chemical and physical properties. And so they will have repeated periodic physical properties that end up, if you go downwards in these vertical columns, into a pattern, which is those groups. Okay? For example, we have, let's say, the group that contains copper, silver, and gold in it. Now, all of those are jewelry metals, right? They're all very shiny. They don't corrode very easily. They all conduct electricity well. Notice they have many of their properties that are similar. Periods then are going to be the horizontal rows in the periodic table. The elements in a period demonstrate a range of properties that go from metallic, which is on the left, to nonmetals, which are on the right. Okay, so valence electrons. This is going to tie in later once we have gotten into the electron configurations, okay? So valence electrons are going to be the electrons that will be on the outermost principal energy level of an atom. So these electrons are going to be the ones that you gain or lose. Much like you don't interact with stuff using the insides of your body, you interact it using your skin, right? Your outer parts of your body. An atom is going to interact with everything using the outermost electrons. Those outermost electrons are always the valence shell, or valence electrons is referring to electrons in the valence shell. And remember, that's because that's the highest energy level, that's the highest shell number, that is the furthest out from the nucleus. Elements in a group or family have the same numbers of valence electrons. That's actually what gives them the repeated chemical properties that we were talking about. It's because they literally look alike on the outside. Inside, they have different numbers of shells, sure. But outside, the last shell, the outermost shell, they all have similar numbers of electrons, and so they look similar. So some of the groups in the periodic table that have special names because they have some special properties are alkali metals, which is group 1A, alkaline earth metals, which is group 2A. So if you look at the very left part of the periodic table, group 1A is that stuff to the left. Lithium, sodium, potassium, etc. Alkaline earth metals are group 2A, it's the next one over. And this has things like magnesium and calcium. Halogens is the second to the far right. So you look at your periodic table, look all the way to the right, and then go one over to the left, group 7A. And these are going to be your chlorine, fluorine, bromine, etc. Now, noble gases are the ones that are all the way to the right completely. And they're going to have things like helium, neon, argon, etc. So metals, nonmetals, and metalloids. These can be considered the large group or over groups, okay? The overall groups. The metals all have similar properties to some degree, which is their metallic luster, that, metals are shiny. That's what luster means, that they're shiny. They reflect light well. They conduct heat and electricity fairly well. Some of them conducted extremely well. Some of them only conducted okay, pretty well. They're malleable and ductile, or ductile, depending on where you come from. Malleable means that you can bend it. So if you've ever taken a wire and bent it back and forth, that's malleable. Ductile means you could pound it out into a sheet. So you can take a hammer to it, pound it on a sheet, and literally means that you can make a duct, like an air conditioning duct out of it. That you can pound it on a sheet, bend it up, and make a duct to put stuff through it. So if you can pound it onto a coin, it's ductile. Some of these examples are things like sodium, copper. Of course, steel is an alloy made out of iron that shows metallic properties as well. Non-metals, these have a dull luster overall. The non-metals, the best thing that can be said about them is they are not metals. Okay? So they're not going to have many of the properties that metals have. That means they don't have a metallic luster, they have a dull luster. They tend to not be very conductive to heat or electricity. They tend to be brittle when they're in their solid state. Brittle meaning that you could take a hammer to it, and if you hit it with the hammer, it would smash. It would not bend to it. For example, the example that most people find sticks in their head quite a bit here is a diamond. So if you were to take a diamond and you put it on the ground and took a hammer to it, you would actually crack that diamond into pieces because it's brittle. It's very hard, but it's also brittle. Okay? Whereas steel would get scratched up by the diamond, but you can bend it easily. Copper you can scratch with the diamond because it's not very hard, but you can bend it all day and it doesn't break, right? You could smash it with a hammer and it's not going to shatter, it's just going to bend. And so some examples of nonmetals are going to be sulfur and bromine. Many of you may have actually seen sulfur before. It's like this yellow powder substance. Most of you probably haven't seen bromine before, though it's a very kind of pretty orange color. Anyways, metalloids. These are going to be the things that aren't quite metals, but they aren't quite non-metals either. And so metalloids will demonstrate some of the properties of both metals and non-metals. And so some great examples are things like silicon and arsenic. Silicon's the one you guys probably have some idea of. If you ever looked inside of a computer or saw a phone or computer or anything like that when it's broken and seen the circuit board, that's silicon. That's a semiconductor they used in computers. And so silicon is kind of shiny. It's a semiconductor, meaning it conducts under certain conditions, but doesn't conduct very well under other conditions. So kind of half in between, right? And it's a little bit malleable, but not super. You can't bend it very far. So it's a relatively brittle compared to a metal. So it's sort of, on the border between. And that's the best that can be said for metalloids. They tend to be sort of, one or two properties like metal, one or two properties like non-metal, or somewhere in between those. Okay, so this right here is how your periodic table actually breaks up if you talk about the electron configuration. And so this is your periodic table. You will notice this one looks a little bit different than the periodic table I give you on the Google Classroom, or a periodic table you'd look up. And the reason for that is your normal periodic table has this F block here, which are called the inner transition metals, or the lanthanide series. That has that down here, actually. And it shows a little arrow that points up between your transition metals, which are here, and your S block here. your alkali and your alkaline earth metals. And so a normal periodic table, this would just be directly abutted against this yellow portion. So the red goes directly to the yellow, then to the blue. And the green part here gets put down the bottom. And they do that so that it fits on a piece of paper. You can see this is actually quite long. They used to actually add into books and stuff a fold out periodic table that you could literally fold out. But they kept getting ripped and some people never had them. So they got rid of those. Anyways, if you ever look up periodic table online, you can actually find expanded periodic tables that are like this with the elements in them. So you may notice here that I have this labeled, don't I? Where it says S, P, D, and F. So if you use a periodic table, this shape is made due to the electron configurations of the atoms. And so your S subshell is right here. It's these two first slots. Those were your S subshells. So this was your S subshell this entire time. And so when you are on the second energy level, you are a 2s that you're filling up. That's what you're filling up in orbital-wise. The S subshell has a single orbital in it, and so you can always tell how many electrons an orbital has in it because there's 1, 2 slots. And that's literally what you're seeing. You're filling up those 2 slots in your S orbital here. So 2s can fill up 2 electrons into that orbital. Now, if you go across now, you'll see that you're going to hit your P block. And literally, that's what that means. These right here has 6 elements going across. That represents you can fill it in with 6 electrons. Those 6 electrons are filling in 3 orbitals with 2 electrons each. So 1, 2, 3. And those 3 orbitals are your P orbitals that you're filling in. And so you fill in your P orbitals one at a time. 1, 2, 3, 4, 5, 6. So at this point right here, you have 1 electron in your P orbitals on your second energy level. So it'd be 2p1. This would be 2, right? So you're filling in 2 electrons at this point in your P orbitals. So it'd be 2p2. And so on. Once you've filled in 6 electrons, you are your noble gas. Noble gases are noble gases because they don't react with anything else, because they have full electron configurations. They're completely full for that energy level. Now, once you get to this point, to give it more electrons, you have to go up to the next energy level. Because remember, it's like floors, right? You fill in the lowest floor first, and then you start working on the second floor, the third floor, the fourth floor, so people don't have to walk as much. And so you go to your third energy level now. Your third energy level will again be that third shell, third period, third energy level. Again, you start on the left, and that means you're filling in your S orbital first. So you fill in your 3s orbital. This is 1. This will be 2 electrons in that 3s orbital. And then again, you're going to go across, and you'll hit your P orbitals here. And so you fill in your 3p orbital. And once you have that completely full, you would go down here to your 4th orbital, your 4th energy level, and fill in your 4s orbital. Now, the one bit of a curveball is you may notice that some of the rooms do not get used on the first floor of our building, and some of the rooms don't get used very often on our second floor of the building. And those are because those rooms are awkward, right? They're weird. They're difficult for people to use as classes. They're high energy, if you will. Okay, so the d orbitals, these are higher energy. They actually get made up here on your your third energy level, is where your d orbitals actually get made. But they're so high energy that they'll only ever get used after you've used your 4s orbital, because that's a better room. People like it more. It's less energy to use it. So after your 4s orbital is filled, you'll start filling in your 3d orbitals. Again, the easy way to remember this is you're on your 4th period. D's are uncomfortable, so it's always one less. So instead of being 4D, it's going to be 3D because they're uncomfortable. And so this is 3D orbitals that you start filling in. How many orbitals are there? Well, all you have to do is count along. So there's 10 elements here. That means that there's 10 electrons that can fill into these 3D orbitals. And that means there's 5 orbitals. There's 5 3D orbitals. Now, once you've filled all of those up, you would then start filling in your 4p orbitals. And so on, and so on. Now, once you get down here to the 6th period, 6 energy level, you fill in your 6s orbitals, your 6s orbital, and then the next one over is going to be your f's. Now, f's are even more uncomfortable. So they're always going to be -2, meaning at the 6th energy level, you're filling in the 4th energy level f orbitals. So another way of thinking that is at the 6th energy level, you're going to be using the 4f orbitals. Now, you fill those up. If you count along here, you'll see that there's 14 spots here. There's 14 elements across, and that's representing the 14 electrons that you can put in these orbitals. And so that means there are 7 f orbitals that can fill in 2 electrons each to give you 14 electrons filled in to your f subshell, or your f orbitals. Now, once you have those full, you can then start filling in your 5d orbitals. And then once those are full, you can start filling in your 6p orbitals, much like the different rooms in a building, right? And so let's go ahead and try doing nitrogen real quick. So I want you to get your periodic table. Now, let me say and mention, you may have noticed if you looked at this PowerPoint beforehand that I had this stupid triangle thing that you have to fill in, and that was really just a reference to what many other teachers might have taught you before in this. A number of high school teachers that attempt to teach this, they'll teach you this triangle method. I have had a number of students in the past try to argue that they really like that method. It's a great method because their high school teacher taught them it. And of the people that have tried to argue with this, I once had a group of 4 people sit down and they tried, every time people try to argue this, I always say the same thing. Well, then show me. Prove it. Because I'm an experimental sort of person, right? So prove it. And I once had a group of 4 people try to do this all at the same time. What they did is I sat them down. We sat down for almost an hour total for the entire discussion. And in this discussion, I gave them 5 examples that I said, okay, try these 5 out. And they were just straightforward, easy things, like one of them was nitrogen, actually. And of these 5 examples, these 4 people that were so convinced their high school teacher had taught them this correctly, and that, man, they knew how to do this, and their method was superior to what I'm teaching you right now, that, you know, my method's ridiculous, takes so much time and effort, and their method was so great. These 4 people got all together, one of them managed to get one of the 5 questions correct using their method. Of those 4 people, they got 4 of the questions wrong. Actually, 3 of them got all of them wrong. One of them managed to get one of them right, and of that 5 questions. So one of them managed 1 out of 5. That's really bad. And it took them over 30 minutes to do this, to work these questions out using that stupid triangle method that just is like saying, I'm going to take something straightforward and easy that I could just read off the periodic table, and instead I'm going to write out 20 things on a piece of paper and, you know, make 20 times the effort and 20 times the work. So when you do these, what you should always do, how you should do it, is you should always just read your periodic table. So you get out your periodic table, and I'm going to go ahead and do that real quick, so please excuse the abruptness. Okay, so now you can see I have simply gotten out my periodic table, just as if you were doing this at home, right? And we're going to try doing nitrogen. So all you need is your periodic table here. You don't need anything else. You don't need to look at anything else. All you need to do is just find nitrogen on your periodic table. There's nitrogen. Okay. So what we're going to do is every single time you do an electron configuration, all it is an address on the periodic table. So we start at the beginning, much like you start at the beginning to find anything. And that first line right here, that is the first energy level, isn't it? So we will start with 1. The first thing that pops up on the first energy level is S block. And so it is 1s. We are past this, we're completely full here. So this has to be 1s2 because we're past this. We're down here that we want to be. So we are 2 electrons in our 1s orbital. And so 1s, first energy level, s block, 2 electrons in it. So 1s2. Now we go to our next energy level, 2. This is the s block, so we put s. There's 2 electrons. We're past this, so that's 2. So we have 2s to the second power, representing that has 2 electrons in it. Now the next one we hit here, we're still in the second energy level, but this right here is the p block. And so this is going to be 2p. We're 1, 2, 3 positions in, meaning we have 1, 2, 3 electrons in our p block. And so we put 2p3. Notice that is your electron configuration. Now, this part right here, this is your valence shell. This right here is what would be called your inner core electrons. So right here in our previous example, this 1s2, this represents your core electrons. Those are the inner shells, the stuff that don't react with anything, the electrons that aren't going to get removed or added. This right here, these are your valence shell. And so these electrons are the ones that are on the outside, the ones that will get reacted, the ones that will get taken, okay, or added to. And so that is your valence shell with your valence electrons in it. Okay, let's go ahead and try a couple more of these. Right here, this is just a table. What you can do is, if you want a little quick practice on this, you can actually just look at one of these, cover this side up, and try to generate these yourself. And then you can double check against these. And so let's go ahead and do something a bit like carbon, and then we'll come down here a little bit. Okay, so again, we would go for carbon. Carbon is C right here. And so the next part we do is, again, we just start at the beginning and we work our way down to it. And so again, this is the first energy level, 1, S block, and 1, 2. So 1s2. Next, we're in 2, second energy level, S block, and then we're 1, 2, because we're past this. So 2s2. And then this will still be the second energy level, but this is your p block now. So 2p, and we're 1, 2 positions into it. So this will be 2p2. And that is the answer for that. Okay, so let's go on to another energy level real quick. Let's go to something like sodium. And so we go to sodium here, Na. So this right here, we again trace from the top, start at the top, and work our way down. So 1, S block, 2, because we're past this. So 1s2. 2s, 1, 2, so 2s2. And then again, we have this full again. So this has to be 2p, there's 6 of these, 2p6. Okay, now we can go to the next energy level again. And we notice that that's right there, so that we're just going to fill in the first one. And so again, that was 2p6 that we just did. Next one's 3s block again, so 3s. We're 1 position into it, so 3s1. And that's it. And that's all you have to do. It's actually just that simple. You can just read it off your periodic table. The funniest thing is you don't really have to remember much, because how many electrons are in an orbital? Well, you just look at your s block. There's 2. 1, 2. How many electrons can you fit in p orbitals in your p blocks? 1, 2, 3, 4, 5, 6. How about in your d? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. You can literally just count them off of your periodic table. You don't have to memorize anything there. All you need to do is understand what you're reading. And so that's how you can really cut down on the amount of work you do. Anyways, let me know if you had any troubles with that. Again, this is a great opportunity to ask me any questions if you have any questions on this. Okay, so one of the things that you might have heard of before is sunlight is an abundant source of energy. It is. There's a tremendous amount of energy that's hitting the earth every second of every day from the sun in the form of what we call sunlight. And plants store this solar energy as chemical energy via a process called photosynthesis. An interesting side note to this, by the way, is photosynthesis used to be the most efficient form of gathering this energy. About 5 to 8 years ago, we came up with solar panels that were more efficient than the plants. So that's no longer true, which is a good thing. Solar plants, by the way, use almost exclusively visible light, which is a very small amount of the sunlight that hits the earth. New solar panels use larger amounts, larger spectrums of that light. And that's why some of the solar panels are getting actually very impressive. And if you ever are curious, there's the different types of solar panels, like cloudy day solar panels, bright sun conditioned solar panels. These take different frequencies of light. They take different energies of the light, different wavelengths that I've been mentioning. Anyways, this is a sort of interesting thing. Artificial photosynthesis, this can be used to generate hydrogen fuel. And so this is one of the things that's been worked on quite a bit lately, is an artificial form of photosynthesis where you would use sunlight to generate hydrogen and oxygen. Use these then in hydrogen fuel cells. And you can actually see applications of this that get deployed a lot for like, oftentimes like if people's houses are wrecked and they have to put people in temporary shelters, they'll use hydrogen fuel cell artificial photosynthesis essentially with a hydrogen fuel cell to give those people power. Those towers that you see a lot, that's actually what a lot of them are. Anyways, this is the photosynthesis a plant does. It takes carbon dioxide, water, and sunlight, and it uses it to make carbohydrates, the sugars, and oxygen, which is what we breathe. Hydrogen fuel can be reacted with oxygen, produce heat and electricity. The great thing about this is the product it makes is water. And water is about as benign as you can get with any substance on Earth. An interesting side note, by the way, is water is actually a greenhouse gas. It is actually the most effective, the largest part of the greenhouse effect that is causing global warming is actually water, but it is not something we can control going into the atmosphere, and so we typically ignore it. And in fact, it's just not something we can actively do anything about. And that's why we concentrate on methane and CO2 and such, okay? But if you ever want to do a little discussion in that, I know way more than I really need to about global warming, greenhouse effects, and everything else. I'm actually to some degree an expert. Now, water, you would use solar energy to break the water apart. That would make hydrogen and oxygen. You then react those to make heat or electricity. Typically a hydrogen fuel cell would make electricity, and it would give you water again. And so this cycle for hydrogen fuel is very, very nice and clean in its products and reactants. The reactants react very easily to form water in the atmosphere, so they're not particularly dangerous. And at worst, they would give you oxygen that you can breathe. So the only bad thing about hydrogen fuel cells is the hydrogen fuel cells themselves can oftentimes be made out of things that are either rare or can cause issues if they get released in the environment. So that's the only bad thing about hydrogen fuel. Anyways, you guys take care and let me know if you have any questions.